using PSS 2.0 hardware-software interface to validate 4G, 5G forward error correction encoder, decoder, IP in emulation and silicon. Abstract. For effective validation, it is critical to have a test framework which can be seamlessly scaled from IP level to subsystem level to SOC level test cases. The PSS 2.0 standard introduced the hardware-software interface HSI as part of the core library, which provides a representation of the register. The HSI layer enables users to write a single implementation of device driver logic. In this paper, we discuss how we used the HSI layer to enable vertical reuse of the tested content across platforms. Introduction. One of the key driving factors in the development of the PSS standard was the need to describe test content as a higher abstraction level, enabling seamless executing across different verification platforms. There are multiple platforms that are used throughout the verification, simulation, emulation, FPGA prototyping, and silicon, to name a few. And each platform might use a different language. The scope of the verification also varies across the platforms, from IP level to subsystem to SOC level scenarios. Based on the current industry trend, the methodology of choice is UVM test benches on IP subsystem level on simulation platform and C driver based tests on embedded core based environment running on emulation or silicon. This create a portability wall as shown in figure 1, as UVM sequences cannot be run in embedded cores and C driver code cannot natively drive UVM test bench. Figure 1. Portability challenge across platform. The PSS 2.0 release introduced the hardware-software interface as part of a core library. HSI abstraction the mechanism of lower-level register access. HSI provides much more than simple register abstraction. It provides a representation of memory, registers, interrupt, synchronization, and so forth, enabling efficient way to implement driver logic, so the HSI sequences can be mapped to the different target implementation by the PSS tool. In this paper, we provide an overview on how to adapt HSI into a PSS methodology. So, section 2, PSS HSI development flow. Figure 2 captures the steps involved in generating a PSS test using HSI sequences. Figure 2 PSS HSI based development flow. A. PSS register definition. PSS tools may provide an register automation required to convert the standard register description formats like IPExec into PSS HSI register models. At Intel, we use a custom XML format similar to IPExec for register description, so a custom script was developed to convert this XML format into HSI register. So, code snippet below shows a basic register description. Here, the registers are defined under the component IB_, DMA_, MEM_C. The leg underscore group underscore C component is the base type for specifying register groups. Register underscore C is a parameterized component base type for specifying the programmable registers of DUT. Component register underscore C is parameterized by a type R for the value referred to the register value type that can be read written from to the register, which can be 1. A packed structures type that presents the register structure. 2. A bit vector type in bit n. Kind of access allowed to the register, which by default is read-write. Width of the register SG and number of bits, which by default equals the size of the register, value type R rounded up to a multiple of 8. The leg underscore C component provides read function, read underscore var function, read write function, and write underscore var functions, which may be called from the test realization layer of a PSS model. Being declared as target functions, these need to be called an execute body context. Instantiating the register structure within the component prevents namespace collision. B. Associating register group with the address regions. Before the read and write functions can be invoked on a register, the top-level register group under which register object has been instantiated must be associated with an address region using the set underscore handle function in that register group. An example is shown in the code snippet below. Writing on HSI sequence. Once we have a register group instantiated in our PSS model, we can write our HSI register sequences. Code snippet below shows a simple HSI register write using the write function. In the code snippet, reg underscore inst is a reference to the register structure we plan to write into, and it is updated with a randomized value in post underscore solve. D. Target code implementation. When we talk about target code implementation of HSI sequences, it is important to point out the PSS standard does not impose specific rules on target code implementation. PSS tools are free to implement their own way of generating the target implementation code. The target code shown in this next section is specific to the PSS tool used at Intel. 1. HSI2 UVM target implementation. The PSS tool generates C host code which drives transactions on the UVM agent using SV DPI calls. The tools also generate requires SV integration code to map these functions to the target. The generated C host code for our simple register write looks as follows. The PSS tool also generates an SV stuff file which creates a task write underscore scalar function method that is exported as an DPIC core, and this task maps to the lower level UVM sequence. The code example below shows the SV integration. The host code is forked off from the run phase of the UVM test. 2. HSI2 embedded C target implementation. On core-based environment registers are accessed using direct memory pointer-based accesses as below. Third, forward error correction design block. As a communication service provider move from 4G to 5G network, many are adopting virtualized radio access network via WAN architecture for higher channel capacity and easier development of the edge-based services and applications. vRAN solutions are ideally located to deliver low latency services with the flexibility to increase or decrease capacity based on the volume of real-time traffic and demand on the network. One of the most compute-intensive 4G and 5G workloads is RAN layer -1 L1 forward RAN layer 1 L1 forward error correction (FEC), which resolve the data transmission errors over unreliable or noisy communication channels. FEC technology detects and corrects a limited number of errors in 4G or 5G data without the need for retransmission. FEC is a very common function that is not differentiated across vendor implementation. Since the FEC acceleration transaction does not contain cell state information, it can be easily virtualized and enabling pooling benefits and easy cell migration. The figure 3 shows a block diagram of the FEC IP. Figure 3, indicative IP integration diagram. The IP is exposed to as a PCIe device to host interface and provides multiple virtual functions VFS to the host interface. The IP also contains multiple instances of the 4G and 5G encoder and decoder blocks. So these multiple instances of the design blocks basically implied multiple instances of the register files. For example, the PCIe configuration spaces a space for each of the virtual function or registers corresponding to each instance of 4G and 5G encoder and decoder blocks. This is where PSS constraint randomization works very well with HSI sequences to provide an efficient way to write driver code. So we shall discuss this in detail in the next section. Section 4. Our experience deploying a PSS and a PSS HSI. In this section, we elaborate on how we deploy the PSS on our design and the features of the language which were useful in creating test scenarios. A. Register file instantiation and address factorization. The first task is to instantiate the multiple instances of register files and set address map of each instance. The code snippet below shows the instantiation of a few of the register blocks. To make the PSS code more reusable, IP configuration parameters like number of virtual functions can be factored out into constant variables like num_of_vf, so that the same model can be reused in a different region of the IP, which has different configuration parameters. Similarly, the base addresses of the register blocks can be factored out into a CSV table. Capturing the address offset in such a way helps with a vertical reuse. The register offers will be different on IP level platform compared to a SOC level environment. PSS helps in factoring out these configuration parameters. B. Handling non-contiguous register arrays. The IP block contains multiple register arrays where the registers themselves were not contiguous but had a fixed offset between each register. PSS allows adding a constraint on register instantiation to handle these offsets. Here, every register index has an offset of hex8, and for each block or x8, and for each block set correct offset for every index item. C is combining PSS randomization with HSI sequences. The randomized configuration generated by the PSS tool can be incorporated into a HSI sequences. Below code snippet shows the interesting register write. Here the eventual register write depends on two configuration parameters, VF_ID and Q_ID, and HSI provide us an efficient way to write such sequences. D. Incorporating interrupt service routines ISRs into a HSI. HSI enables writing interrupt routine using the wait and emit APIs of the PS event. The code snippet below shows the way to write your interrupt routine in PSS. So, the wait functions act as an implicit yield statement on calling thread. The control flow switches to any other concurrent activity scheduled on the thread. The thread gets unblocked once the emit function gets called from within the ISR. E. HSI and efficient target code generation. While target code generation semantics is mainly left to the PSS tool provider, we felt it is worthwhile to discuss how PSS can generate efficient code. Consider the following code snippet. Here, the generated code will only write those virtual functions which enable the scenario which capture the variable vf_en_list. The generated code only contains very directed code which contains programming sequences very specific to the randomized scenario. This helps in keeping the code footprint small and helps while debugging your test case. The traditional test methodologies usually consist of a driver code and the test case is a separate entity which calls the driver APIs. HSI blends the driver and test cases into a single homogeneous test file. Another HSI API we found very useful was ps_event.sync, which adds a synchronization point between concurrent threads. Adding a sync point between the IP in configuration and data transfer phase helped us thread the design effectively. 4. Result. Adapting HSI into our PSS methodology enables us to reuse test cases from core-based environment, reducing the time taken to develop test content by 70% compared to our previous methodologies. PSS also helped us generate a richer set of the test scenarios with more concurrency and stress added into the mix. It also enabled the pre- and post-sci teams to collaborate on the test development, coming up with a commercial test plan. PSS also enables quicker coverage closure compared to traditional methodologies. Adopting PSS HSI also helps the user to get the most of each environment from an overall verification standpoint. The PSS model and HSI sequences can be developed on IP-level environment, which provides quicker turnaround time in the development phase. Shorter and basic functional test scenarios can be run on IP-level simulation environment, and more complex and stress scenarios were run on emulation and post-silicon. 5. Conclusion. This paper provides a basic overview on how one can adapt HSI into their PSS methodology. We believe this can help accelerate the verification cycle while adding a lot of quality into the generated stimulus. We hope this paper encourages others to adopt PSS into their verification arsenal. Thank you. I read the paper, DVCON paper about the title was Using PSS-2.0 hardware software interface to validate 4G 5G forward error correction encoder and decoder IP in emulation and silicon. Thank you for your time and see you next time. Thank you.